everyone. Welcome back to day 2 of the kickoff for the brand new Ecosystem podcast. Thanks so much for joining us today for our IMS pregame blitz. As you may know, next week in Denver, there's going to be the International MicroApp Symposium, which I will be attending. And this week we are featuring great subject matter experts that will either be featured there or their company will be featured there, and that they have something to offer to teach you as you look forward to next week's event. Before we get started, I want to say thank you to our media sponsor, Signal Integrity Journal. I put a link to the show notes for a free subscription for you. It's a wonderful magazine and source for online resources, education, webinars, and so much more. All their content is peer-reviewed, and they focus on SI, PI, EMI, and EMC. So make sure you go to the show notes and get your free subscription today. Today's guest is none other than my dear friend, John Coonrod, who is the Technical Marketing Manager and Materials Expert Extraordinaire. We're going to talk about 3 MicroApp sessions that he's doing, and particularly talking about a new 3D printable dielectric that Rogers have come out called Radix. So let's jump into our conversation with John. Enjoy. Hi, John. Thank you so much for joining us today on the Ecosystem podcast. We're always glad to see you and glad to learn all the exciting things that are happening at Rogers and all the interesting things you have to teach us. So
thank you. It's good to be here.
It's good to be with you, my friend. Can you, for the 3 people in the world that maybe don't know you or haven't seen your 9,000 webinars and whatnot, can you give us a brief overview of your title, what you do at Rogers, and sort of your background in the industry?
Well, sure. So my title is Technical Marketing Manager, and the title's a little deceptive for what I do. And really what I do, and the group that works with me, is we are a technical resource for the marketing department. And our marketing department is very much tailored and geared to be close to the customer. So a lot of things that we do are more customer technical support for the marketing department. But we also do some marketing in the sense of writing articles for trade magazines, and also we'll write some blogs and present at trade shows and things like that. So along with that, I also do a lot of RF evaluations internally. So I look at our materials and materials in development, and if I can get my hands on competitive materials, I take a look at them. So I do a lot of different RF studies. I'm also on the IPC committee that defines test methods, and I'm the chair of that committee. So we look at different test methods, and we've been trying to find a good test method for testing materials at millimeter wave frequencies, but it's not that easy, unfortunately. But it keeps me busy.
Yeah, no kidding.
Yeah.
Well, I know because I got that one awesome tour of your lab, and I know you have technical chops, and it does seem, you throw that marketing word in there, it is kind of deceptive.
Yeah.
But anyone that really knows you knows your technical chops.
Yeah.
So thanks for joining us for this kind of IMS pregame blitz we're doing this week. And
Sure.
When I reached out to you, I found out you're doing 3 really brief talks in the MicroApps Theater on the floor of the International MicroApp Symposium next week in Denver.
Right.
And you briefly talked to me about a brand new material that Rogers come out with that's very exciting. It's a 3D printable dielectric.
Right.
So can you tell us a little bit about Radix and
Sure.
and what it does and so forth?
Right. Yeah, the Radix is the newest product that we've introduced to the market, and it is 3D printable, as you've said, but there's been a lot of 3D printable materials on the market for years and years, but most, actually all of them that I know of, do not play very well at higher frequencies. So they don't have dielectric constant that's well controlled. They don't have dissipation factor that's well controlled. Moisture absorption is usually high. CTE, it goes on and on and on. So a lot of the things that you're really concerned about for millimeter wave and microwave type applications, the normal material that you'd use to try to 3D print a RF concept is not going to work very well. So the Radix is something that we developed to be 3D printable and does have good RF control. or RF properties. So we control the dielectric constant very tightly. It's at 2.8. We also
Wow.
control the dissipation factor at 0.0043. And what's interesting about the dissipation factor is it seems like the material has very low dispersion in the sense that as you change frequency, the properties do not change much. So the dielectric constant does change a little, like all materials do, as you
Right.
go up in frequency. And dissipation factor also changes a little, as all materials do as you go up in frequency. But in this case, from 10 gigahertz to 24 gigahertz, we see a difference of 0.0043 to 0.0046. So
Wow.
that's
So
really
it's very
good.
stable.
Yep, extremely stable. So it's really good for RF performance, and the moisture absorption is very low, which means it's going to be more consistent in whatever environment that that it's playing in.
So what is the medium like? What is it made of?
Yes, it is a
Or can you
photopolymer.
tell?
Actually, I don't know if I could tell if I knew.
I don't want
But I know the basics of it. It is ceramic filled. It's a photopolymer, and it's curable by UV and things like that. And the type of 3D printer that would be used to print structures with this has to be very specific, and it would be a, a 3D printing process like it's a DLP, digital light processing. That's one process, and another one is SLA. SLA stands for stereolithography. So those two type of 3D printing processes can process the material. And we're working very closely with a company that does 3D printing in high volume and very high resolution. And the company is called Fortify, and they're out of Boston, Massachusetts. So
it's, let me get this
yeah.
straight. So it's a liquid, it's a
Oh yeah.
liquid ceramic loaded
Right.
polymer.
Right.
Now, does it sort of cure
Yeah. You
as
have to
it's
go.
being built up?
No, actually, as it's being built up, it's kind of like a green cure. It's not fully cured in crosslink, so you do have to expose it to UV. But
Okay.
all that's done at Fortify, so it's one of those things that you would draw up what you'd like in some kind of 3D CAD package, send it off to Fortify, and tell them to use the Rogers Radix material, and they will make the 3D structure and cure it and everything, and you'll get your little RF structure to play with.
Interesting.
Yeah,
Now, is the material conductive or
no,
no, it's
no,
not.
it's a
So how does
dielectric.
that work? So it's
Right.
just the dielectric. Okay.
Yep, just a dielectric material. And there's also another company we've been working with, Evertech, and they are using a process that's friendly to this 3D printable. It's actually able to print 3D conductor geometry, which is really cool. So
Can you
now,
explain that a little bit more?
no,
No, you can't.
no.
Okay. See,
Actually, I can
you're
a
no
little.
fun.
I can a little. So as I understand the process, what they're doing is a process that is applying a film, not a film, a catalyst to the substrate. In this case, would be
Okay.
our Radix, and then they will use laser imaging to image what they want, or basically, I think it polymerizes whatever's there, and then as you plate that up with copper plating, what's been affected by laser plates up, and things that doesn't plate up. And I think you probably got a little bit of background as I'm talking on this subject,
Well,
and
I
you
was
may
like,
know
are we
more
talking?
about this than I do.
I'm like, are we talking about a Veritech and Terradun? Because I've been seeing
Right.
3D structures that Veritech has been posting on LinkedIn and
That's it. Yep.
on your material.
Yep.
Okay. All
Yeah.
right. I'm
And that works
catching up
really
now.
well. But what's really cool about this 3D process is you can do so many things with it that it just opens up the realm of possibilities for the RF engineers now. So as you build up a structure, basically from floor up, you can actually build it up with built-in vias, you might say. So you could actually have via holes that come up with it. And then as you plate through the circuit image on the outside, you can plate through the holes too. Now, I don't think
Wow.
it's quite as simple as that for the plating, to be honest, but it is doable. But there's a lot of fun things you can do with this. So besides having the capability to have something 3D printable in large volume, which is nice, it's also, for me, when I come up with these strange RF concepts, it's really cool to be able to send off a concept and have it printed and come back and play with it a little bit. And then you can make some changes quick and easy. And it's a lot quicker and probably cheaper than prototypes for normal printed circuit board technology to kind of define the concept. And then
Have you looked at the sort of cost trade-offs? Like, is it easy? I bet most people are listening. It's like, yeah, but how much does it cost?
Exactly.
But right.
Right. Yeah, actually, I don't know the cost differences between doing something in 3D printable compared to printed circuit board. And well,
I
some of the
mean, it
things
seems like it would be,
I
but
think so too, but
yeah.
I guess I kind of see it as for prototype stuff. You could just have a lot of fun with it and check out different RF structures and see how they work. But it is
S-
capable of high volume manufacturing too at Fortify, so we are
That's
able to do that
exciting.
too. Yeah.
So, um, I know it's early days yet, but what kind of applications are sort of novel things
Oh
as
yeah.
you think about, oh, what can we do here? And
Sure.
or talking to maybe people that are helping you with the
Hmm.
customers that are kind of dreaming, thinking this through. What
Right.
kind of things that you can do with
Well,
Radix?
there's a lot of fun things. Like one is as you basically build up the structure, you can build it up to have cavities built into a circuit. And these
Mm,
cavities can be different sizes and things. So you can basically build a cavity filter that is built into a circuit. Or
wow.
another thing that's really interesting, and we have a demo on this, is something like a Lindbergh lens. And that lens is using the gradient index technology. And what all that means is we are able to, just by the 3D printing process and defining the features, you can actually have a ball, let's say, that at the middle of the ball is a solid core with a DK of 2.8 in this case. And then as you print out from there, then you would have an open lattice, you might say, with bigger openings as you go out. So at the
Hmm.
middle of the core, you'd have a DK of 2.8. And as you go out in layers, it gets less than that, all the way down to 1.1 as possible. So you could
Wow.
have a varying DK in one structure from 2.8 to 1.1. And when you do the right stuff with the right lattice structures and things like that, you can actually build up lenses for antennas that really helps the directivity, and gain can be affected. And there's a lot of good things that can come out of that, actually.
So, John, for people who are listening, when you think of specific applications, you mentioned, directing an antenna,
Hmm.
say, like what other applications do you think would be good for consideration besides proof of concept
Oh, yeah.
is really valuable?
Oh yeah, absolutely. Yeah, the GRIN, the gradient index technology is really interesting because you can do a lot of things with it. So you can use it as a radome on a flat patch, radiant elements, flat patch antennas, and you can actually focus the energy more, or you can change the radiation patterns,
Mm.
maybe able to offset some of the side lobes that you don't want. There's a lot of fun things you can do with it. Or you can just use it as a plain radome too. We also have customers looking at it as a enclosure for a millimeter wave circuit. So it would act as a radome, but also an enclosure too. And if you're concerned about spurious modes, you could actually put some unusual geometry inside here that would actually break up the spurious modes. So it would not only be a housing, but it also could cause less interference and things like that. So
Wow, that
there's
is
a
so interesting.
yeah, there's a lot of fun things you could do with this.
So it's early days, like I said, and you mentioned that you're going to give a talk
Oh,
in the MicroApps Theater
right.
at IMS, which
Hmm.
is the theater in the middle of the show floor.
Right.
And I call it speed dating. It's
Yeah.
like you do these quick 15-minute sessions. I don't know how you're going to fit this into 15 minutes, but
It's I can talk pretty fast, but I'm gonna try not to. But there's a lot of information there, and it's more of, I guess, a teaser than anything else, that we just want to throw out the capabilities that are there. And then I'm hoping that we get a lot of questions and things like that. People come by the booth and talk to us. So it
I'm
should
sure
be interesting.
once kind of RF and microwave engineers hear about this, they are going
Yeah.
to start salivating and going, ooh, ah.
Yeah, there's a
So,
lot of neat stuff you can do with it.
it sounds like most of those micro apps are going to be on the 21st. Do you know off the top of your head when this talk is on the
Yes.
Radix?
This one, you're right. They're on all three of my MicroApps on the 21st, and this one is at noon from 12 to 12:15. And
15 minutes, I'm so sure.
yeah, I'm gonna try. We'll see.
That's funny.
Yeah.
For our listeners, before we move forward, I wanted to say thank you to Rogers for sponsoring this episode and partnering with the Ecosystem Podcast to help bring you awesome education, resources, and to help connect you and equip you to do your best work, sort of in a holistic way. And if you're not able to make it to IMS, John has shared with me some links where you can go listen to a 3D printable structures on the Rogers Tech Hub.
Right.
If you don't know this already, John does these quick tech talks. It's called Coonrod's Corner. To join Tech Hub is free, and there's amazing resources in there. So, anybody that, will stand still for 5 minutes, I tell them to go to the Tech Hub. There's a calculator there, there's technical resources there, and it's free.
Yep.
So I'm going to put that link in the show notes. And thanks again
Sure.
for Rogers for helping me get the design and development community educated.
Sure.
So there is also a Radix 3D Dielectrics page on the Rogers website. I'm also going to share that link.
Oh, yeah,
So, John,
that'd be great.
Okay, well, thanks for sharing those resources with our audience. Okay, let's hop over to your second MicroApps presentation, which I believe is on copper foil, which you and I did a really well-received podcast together in the past. So not much to talk about there.
Yeah, right. Yeah, copper foils is one of those funny things when you first get into the industry and you look at copper foils like, it's copper. How much can there be to it?
Right.
Well, there's a lot. So
Yeah.
I'm also going to try to cram in 15 minutes a lot of information on copper foil. So what I'm going to try to attempt to do is give a quick overview of how the copper foil is made, and then the treatments that are used and why. And then after that, I'm going to talk about some of the grain structures and how you actually measure surface roughness, because there's multiple ways to measure surface roughness. And surface roughness is a pretty big deal, especially at millimeter wave frequencies. When you get higher in frequencies, skinned up thinner, you're using more of the roughened side of the copper. So anyway.
I always say it's like the Himalayas.
Yeah, exactly.
When you look at that under a microscope, it's like, no wonder.
Yeah, true.
So, and again, for audience, I want to let you know, if you're not able to attend IMS, and either check in with John at their booth, which is booth 2030 at IMS. I am also sharing another link in the show notes that John did in conjunction with the Microwave Journal. It's a webinar. And so if you're not able to join, I don't want you to miss out. So we'll put that in the show notes as well.
Great.
And don't forget to also subscribe to the Ecosystem Podcast and come visit that website. And I'll put that in the show notes below, because we have a lot more coming your way after IMS.
Good.
Okay, so that talk is also on the 21st. You know the time on that one, John?
I think that one's, I think it's 1:15 to 1:30 if I remember right.
Well, let me look at my notes here. 1:30 to 1:45 in the MicroApps Theater on the show floor.
Okay. Great. Thanks.
All right. Okay, last. I feel like we're speed dating, for heaven's sakes. Okay, let's, in a really geeky kind of way. So your last MicroApps presentation is going to be on a topic you've covered many times, and I've sat through some of them. And some of it I got, and some of it just, went over my head, but is Co-planar waveguide. So what are you going to talk about regarding Co-planar waveguide?
Yeah, that's a topic that just keeps coming up. And I think it's because there's so many millimeter wave applications and new applications coming up more and more, that I think most RF engineers that are, have gone through the schooling and they have the theory understood. What happens is, if they're not familiar with millimeter wave and they may have been using or working on microwave applications, the transition from the lower frequency to higher frequency, they start thinking, I need a different structure, because when you get to higher frequency, you have more things you don't want. You have spurious modes, you have radiation, you have things that happen that is not that problematic at lower frequency. And one way to help mitigate that is actually using coplanar, and specifically grounded coplanar waveguide. And that does work very well for having less problems and noise and issues at millimeter wave in theory. But in reality, what happens is just by the structure of the circuit itself, it has more variables due to circuit fabrication than would, like, say, a microstrip. So the grounded coplanar waveguide is going to be very sensitive to copper plating, thickness differences, trapezoidal effects, and just quite a variety of things. And I think what I have seen a lot in the industry is as people are learning more about millimeter wave, the RF designers want to go to grounded coplanar waveguide, and then they get kind of disenchanted once they get circuits in and start testing the circuits and realize they don't match the models very well. And it's usually because they're not accounting for things that they don't know about. It's printed circuit board related issues. And once you understand that, then you can use grounded coplanar waveguide at millimeter wave and get really good results. But there's just a lot of little tricks you got to know about. And if you know these tricks and you put them in the model, then okay, things are good.
Yeah, for years when I was working at Transline, working with RF engineers, we ran into this over and over and over again. Well, this didn't come out like I simulated. I'm like, yeah, but you simulated traces with perfectly straight sides, and also like you had like sequential lamination, so the copper kept getting built up.
Right.
So all the modeling was off. So
Yep.
I know this is a big deal, so I'm glad to hear that you're teaching it.
Yeah.
Okay, so that one also on June 21st.
Mm-hmm.
You know the time on that one?
Later in the day.
I do if you
3.
don't.
Yeah.
It's at 3:30.
Oh, 3:30. Okay.
I wrote it down just in case.
I think I'll know the
This
times
is
before
not a
that day
test.
comes up.
Yeah, no doubt, no doubt. Well, we did pretty good. I feel like we just had a MicroApps speed session on John Coonrod's IMS plan. So
good.
Well, super exciting stuff. I'm really excited to learn and share with our audience more about Radix, because that sounds like something really interesting.
I have a long list of things that I want to do with that material.
I'll share those images and stuff that I've seen on a Veritech where they're plating on that as well.
That would be great. Yeah, thanks.
Because I think you guys have published stuff about it, and I'm pretty sure Veritech has, because I was looking at it going, wow, that's really cool.
Right.
So, well, John, thank you so much for joining me today, and I look forward.
Pleasure.
I get to see you
in
a couple of weeks
live in person.
I know.
Yeah,
I
looking forward
seen
to
you
myself.
For a while. I know. Yep. I think I got to see you at PCB West. I don't know. I think I've seen you since the COVID fiasco, but it's always good to see you in person, my friend.
Yep, I agree.
And all my buddies at Rogers. So to our audience, thanks so much for joining John and I for this conversation for our launch week of the Ecosystem Podcast. Don't forget to check out the show notes and make sure you subscribe to the Ecosystem Podcast. I'm going to share a link to the Ecosystem Podcast, as well as all the links I've told you about for John's materials. And there, courtesy of our friends at Teledyne LaCroix, they've given us a free ebook by Eric Bogatin for 100 plus tips on PCB design to help your signal integrity. So that's pretty cool. So thanks for Teledyne LaCroix. And they've also provided us with the promo code so you could have 3 months of Signal Integrity Academy for free. And I think that's I don't know. Anyways, it's, like a $300 to $500 value. So thanks again to Teledyne LaCroix. Thank you so much for joining us on our kickoff week and our IMS pregame blitz. John, I'll see you next week. And to our audience, thanks so much for joining.
Very good. Thank you.
We'll see you tomorrow, listeners. And until then, remember to always stay connected to the ecosystem.